So we've looked at an introduction to plotting, visualization. We mainly use the point plot function, and we saw how to use formula expressions to control what exactly gets displayed. Now we're going to look at another aspect of visualization, which is how to visualize variation and density in terms of plots. Okay, so in terms of relationships, we've seen the following. We saw that uh, the mass of a penguin is related to both bill length and species variables. We saw that. And of course, we call mass as the response variable because that's the variable of interest. And then we talk about bill length and species as explanatory variables. Okay, in other words, we are saying that there is variability in mass and that this variability in mass is explained by the variability that we see in bill length and species. Okay, so variability in the response variable uh, is what we are interested in. And we can look at it in two different ways. One is we can look at the shape of the variability, just to get a broad idea of the variability, a visual perspective, and an intuitive feel for how the value is actually distributed across its entire range. And then we look at more rigorous ways of describing variability, or I would say measuring variability. Okay, so in this lecture, we are only interested in looking at the shape, visual perspective, and in later lectures, we'll be looking at more rigorously measuring the variability. Okay, so now we are looking at the births 2022 data set, and we're going to look at first the durations of the pregnancies. Okay, so that's what the duration is. That's the distribution of durations, and of course it's jittered. Okay, there is no x variable at all. We are looking only at the pregnancy duration and plotting all the pregnancy durations possible. Of course, since there's no x variable, they will all fall on a single line. But in order to visualize things better, we have jittered the data. Okay, so clearly we can see that there are many, many points crowded up here, far fewer points here and here. Okay, that's because we've jittered the values and we've also used the point ink option to make the points a little bit transparent so that we are able to see when there's overplotting, how much of overplotting is going on. So very clearly, the pregnancies are distributed around, let's say, 39 or 37 months. They're far more concentrated in this region from about, let's say, 33 to about, let's say, 42. Most of the, bulk of the pregnancies occur in that is the duration of the bulk. Okay, so this actually 22,000 points have been plotted here, and the minimum is 17, the maximum is 47. Okay, so the minimum value is somewhere falling here, 17, and the maximum value is close to about 47. And are they uniformly distributed across the range? Meaning, are the values of, are these 22,000 points, are they uniformly distributed across the range from 17 to 47? Clearly, no, they're not uniformly distributed. There's tremendous concentration in this middle region, and not even middle region, one would say, somewhat to the on the higher side, and very far fewer points on the below and above that concentration region. Okay, so there are many more between 34 and 41, many more pregnancies having a duration between 34 and 41 than outside of that range. Okay, so it's very sparse at the lower and upper ends. Okay, so now what we want to do is to look at the distribution, to visualize this distribution in a better way. Of course, this gives us a certain visualization of the distribution of pregnancy durations, but we want to get an even better picture of this. Okay, so clearly we can see the relative density of points here, but not very much because there's a lot of overplotting going on here. We don't know what's going on. How many points are being overplotted here, how many are here. In other words, out of the 22,000, what proportion is sitting here, etc. That's not very clear from this. Okay, so this is just the points but jittered, and here is the distribution of the points. Okay, now the distribution of the points, what it tells us is, I mean, you can look at one side or the other side, you don't have to look at both sides, it's going to be completely symmetrical. What it's telling you is the height of this thing, uh, that's going to tell you the relative number of points which are in that area, right? So here you can see this is very tall. So you're seeing that a great proportion of points are here at this level, which is roughly probably 37 or 38. Okay. And then as you go away, it slowly drops off and really small, and you can see here it's going like this. Uh, Very small proportion are at these lower ranges. Okay, so you're seeing that the bulk of the values are concentrated in the middle here. Okay, that's what this plot does. This is called as a violin plot, and we'll shortly see why it's called a violin plot. Okay, and it gives us an idea of the distribution. The width of the violin at any point shows the relative density of points there. Okay, so the width is largest here, so we can clearly see that the maximum number of points are actually at 37 or 38, and that keeps dropping off when you go higher and when you also go lower. In most number of points, highest density is at 37 and very low density at the edges. Okay, so what we have done here is we have done the point plot, which is this. This is the point plot, all the points, and we have added on top of it the violin plot to show the distribution. Okay, so we say here that we have annotated the point plot with a violin plot to visualize the distribution better. Okay, so those are the sparse areas of this plot. Okay, why do we call it the violin plot? Well, a different plot makes it even clearer why this is called a violin plot. So here we are taking a data set which is called the Wickham data set. Okay, and here we are saying we want the violin plot of just the variable age. Okay, that's the only variable we are concerned about. We are not concerned about any other variable. Okay, so here is a plot where we are not interested in an x and a y. We only have a y. There is no x. Okay, when you don't have an x, you just put in a 1 to the right side of the tilde. When you're interested in plotting just a single variable, then you use a 1 on the right hand side to indicate that. So here we are saying show me the distribution of age and annotate it with a violin plot. Okay, so here you're seeing here distribution of age. Okay, and when you add a violin plot, it looks like this. This is why it's called as a violin plot. Okay, it tends to look like the bass of a violin, the resonant chamber of the musical instrument violin. Okay, so once again, if we only looked at the jittered points, we won't get a good picture. But here you're getting a good picture. You're seeing that there are two kind of areas of concentration. One is around 50 or slightly less, and the other is here around 30. Okay, so lots of people in the age group here, and then it drops off a little bit, and then again it bumps up and then drops off sharply. Okay, so that gives us an idea of the distribution. Unlike the case of the pregnancy durations, where there was a tremendous concentration of points at one level, here that's not the case. It's much more gradual. It's still not uniform, right? Because there is, variability. We are seeing here there are more points, and then it drops off here, and then it increases here, and then it drops off sharply here. So there is variation, but it's not as concentrated or skewed as the previous one was. Okay, that's just a minor piece of humor on my part. Whoever thought of the name violent should take a bow. Okay, now violent plots are very useful to compare distributions. So here we are doing again within the same Wickham data set, we are looking at the distribution of age for smokers and non-smokers. This data set has a column called smoker, which has a value yes or no. Yes indicating that those people were smokers and no indicating those people were not smokers, right? So we are looking at the age distribution, and we want to look at it separately for smokers and non-smokers, right? That's why we are putting smoker on the x-axis and age on the y-axis. So we'll get a point plot, and we are saying, well, annotate that point plot with the violin as well. Okay, so when you have a categorical variable on the right hand side, your point plot function automatically gives you uh, two violins, right? When you annotate it, we've got these two things. And so we see separately the distribution of age for non-smokers and the distribution of age for smokers. Okay, now the good thing about the violin plot is that the width of the violin, okay, uh, it doesn't depend on the actual number of points, right? So here you see that clearly that there are far more non-smokers than smokers. Okay, so that doesn't mean that just because there are more smokers at this particular smokers at the non-smokers at this particular point, the violin will somehow become wider. Okay, the violin shows you relatively to that group how the distribution is. So it's really good for comparing distribution. So clearly you can see that non-smokers have a wider dispersion of age, and the people are distributed uh, more evenly across the entire spectrum. Whereas for smokers, you see that they are more concentrated on the lower spectrum of age than on the higher spectrum of age. Okay, so there are far fewer older smokers than there are older non-smokers. So for example, here you see beyond this particular age, there are still quite a few smokers, or even in relative terms, a good proportion is at this higher range, whereas here at the higher range, you see a smaller proportion. Okay. Prima facie indicating, of course, that smokers don't live as long, but we cannot clearly say that from this data set because we don't know anything else about how this data was gathered and all of that. Okay, it could simply be possible that that there were some biases in the data gathering and so on. So we can't use this really as conclusive proof that non-smokers live longer, but it's giving you a hint that maybe that's going on. It's worth further analysis. Okay, so here once again we are looking at the births data set, and we are comparing the birth duration for single children as opposed to twins. Okay, so when a birth occurs, right, it could be either just a single child which is born most of the time, or you could have twins or triplets or quadruplets and so on. So here we are only comparing single children with twins, and we are looking at the gestation, the duration of pregnancy for both of those. Okay, clearly we can see a difference in this distribution. For singleton children, first of all, the pregnancy duration is somewhat longer, right? So you can see here that the maximum is occurring here. We earlier saw that this probably is about 38 or so. But for twins, the maximum duration is somewhat smaller. I mean, the maximum number of points occur at a smaller uh, duration period. Okay, that means they are born somewhat quicker than singletons. And the other thing you're seeing here is that for twins, there are many, many more of early births, okay, premature births. So you can see here that the distribution is showing some amount of thickness here and so on. Whereas here you see this has become really thin here. Okay, so for a given duration, you see the relative number of births that occur at that duration is far, far smaller for this, for singletons, than it is for twins. Okay, so violin plots are really useful for comparing the distributions, and this is giving us a good picture of the durations of pregnancies for singletons and for twins. Okay, again, we'll not look at the code here right now. The code is a little bit complex because there's some amount of data processing that's required before you can get this plot. But what we're looking at is the benefit of the plot itself. Okay, far fewer twins. Of course, the number of points here is much, much smaller than this. There are many, many more singleton births than there are twin births. However, the violin plot still shows you the distribution that you can compare across the two, irrespective of the fact that there are far fewer of one than the other. That's the benefit of the violin plot. The width of the violin does not depend on the absolute number of points. Okay, Um, so that's really useful for comparison. Okay, so clearly you can see for twins, the maximum is occurring at 36 weeks. The maximum density occurs at 36 weeks, whereas for singletons, the maximum density is occurring at around 39 weeks. And the variability is much more for twins than it is for singletons. Okay, and also premature births are much more likely for twins than they are for singletons. Okay, now when it comes to distributions, there are some common shapes that we'll encounter. Okay, uniform would look like this, where the points are uniformly distributed across the entire range. Okay, so that's called a uniform distribution. This is called a normal distribution, where uh, it is symmetrical. Maximum number of points are in the middle, and there's a normal bell shape that's going on here, completely symmetrical. That is called as a normal distribution. Sometimes you'll have what are called as long tail distribution, which looks somewhat like a normal distribution, but the tail is longer than a normal distribution. Okay, these are called long tail distributions. Again, it is symmetric, whereas here you've got what is called as a skewed distribution. Okay, the maximum density is not at the center. The maximum density is occurring here, and then uh, one side of the tail is much longer than the other side. In fact, here there is no tail on this side at all. Okay, so these are some common shapes that we'll encounter when we look at distributions. Okay, now there are many skewed phenomena in the real world. So here we are looking at uh, there's a data set called the Monocacy River, and we are looking at the distribution of precipitation at that in that area. Okay, so again, we are only looking at the distribution of precipitation. There's no x variable, so we just put it as a y. Okay, so that's a very skewed distribution, right? So you see maximum number of precipitations are around the lower range, and very rarely do you get precipitation. One is assuming that they've measured daily precipitation. Okay, there are very few days in which you've got extremely high precipitation. Relatively more days in which there is no precipitation at all. Okay, so once again, we are looking at another data set called US wildfires, and we are looking at the area that wildfires burn up. This is particularly topical with the fires in LA. Okay, once again, that's a skewed distribution, right? Most of the time, the area burnt up is small, but occasionally fires go crazy and a tremendous amount of destruction happens. Okay, but it's rare, but it does happen, whereas the bulk is here. So once again, you're seeing here two examples of skewed phenomena that happen in the real world. So normal distribution is common and skewed distributions also occur. So that brings us to the end of our discussion of visualizing variability.